Good morning. So we proceed with our conference today. So it's a great pleasure to introduce Ailsa Keating from Cambridge, who is going to tell us about homological mirror symmetry for log Calabi-Yau surfaces. Ailsa?
Great. Thank you very much for the introduction. Can everyone hear me fine? Or rather, let me know if you can't.
Yeah.
I have a small request, which is I've got a setup where I can actually see the kind of gallery view with all the participants. So if you happen to have a camera, if you switch it on, it sort of helps me to just like feel like I'm looking at an audience rather than just looking at a list of names. Hi, Matt. Thank you. Right. So this talk is about joint work with Paul Hacking, which appeared on the archive last spring on HMS for log Calabi-Yau surfaces. So what's the setup? Well, we're going to work with pair YD, which is log Calabi-Yau, so D's anti-canonical. This whole talk is in 2 dimensions as a surface. And I'm assuming that D has maximal boundary. So what that means is for n equals 2 case that for dimension 2 case that D has a node. And in fact, that then forces D to just be a cycle of either a cusp curve or a cycle of P1s. So the goal, in order to prove HMS, is we're first going to construct a sort of suitable mirror space that will then relate to either to known mirror constructions. So the goal is to construct a mirror as a total space of a Lefschetz fibration. So to have a Stein surface, a real full manifold, together with a superpotential to which I'm going to call W, which is going to be a map to C. So M is going to be the total space of a Lefschetz fibration. And I'm calling the fiber sigma. So sigma is a Riemann surface. And we're after HMS statements. So in this kind of relative CY setting, they typically come in a triple. So the first statement here is about the whole of Y, the surface, and that's going to be mirror to, or we would like this to be mirror to the directed Fukaya category of W. So this is an invariant of the Lefschetz fibration of the superpotential. There's a sort of complementary HMS statement about D and the fiber. So perfect complexes on D should be quasi-isomorphic to the sort of regular Fukaya category of the fiber, sigma. Remember, D is singular, which is why I'm working with perfect complexes. And finally, in the sense, the sort of statement that you care about the most is this one here, which is that coherent sheaves on the complement, so Y delete D, for people who often work with sort of GHK type settings, this is the space that gets called U over and over again. And this should be quasi-isomorphic to the wrapped Fukaya category of the mirror M. So morally speaking, in terms of geometric structures, the pair Y comma D is mirrored to the data of the Lefschetz fibration. And if you delete D, you forget about the Lefschetz fibration. So you just have an invariant of M. Oops, oh, I had put that in my slides. So why think about these spaces? Well, a big category of the main source of log CY surfaces, was the generic case, is that D is the sort of resolution of a surface cost singularity. So D is sort of determined by the data of all of the self-intersection numbers. And when you have that data for a cost singularity, there's an algorithm which gives you the dual cost singularity. This is sort of quite classical algebraic geometry. And the idea is that M, my mirror, is the smoothing of the dual cost. So YD, so D is the resolution of one, and M, you see the smoothing of the other. And this is the circle of ideas that come up in Gross Hacking Keel's proof of Lorentz conjecture, which is precisely about sort of when dual cost can be smoothed. Before I proceed, are there questions? Okay. So how do we approach this? Well, a very nice property that log Calabi-Yau surfaces have is that they admit what we call the Tourette model. So what does that mean in practice? Let's start with my YD. So my picture here is the cycle D. Remember, this is a cycle of -1 curves. Sorry, a cycle of P1s. Now blow up a bunch of nodes of D. And let's say you get to Y prime D prime. Notice, by the way, that the interiors don't change when you blow up corners. And now, so I have this Y prime D prime, and I claim that once you've blown up sufficiently many of the nodes here, Y prime D prime is always going to be itself the blow up of the toric pair. So down here, I have Y bar prime D bar prime, which is a toric pair. And then to get to the middle stage here, what you do is you blow up sort of finitely many points on the interiors of the components of the toric divisor. So I blow up interiors of the toric divisor, I get here, and then potentially you just blow down a bunch of boundary components to get to YD. So this is what a Tourette model is. Notice that there's naturally moduli in this picture, right? Because I can just move around the points that I blow up in the interior, and that gives you complex modulus. So today, we're going to focus on a very specific choice, which is when you deform the complex modulus, on the mirror, this corresponds to deforming the symplectic form. We want to work today with exact forms, and the way to get that is you want to blow up a distinguished points on each of the toric divisors. And one way to think about this point is you have a toric action, just fix a specific toric action that gives you a toric action on each of the interiors of the boundary components. You know, they're copies of C star. And now take the point -1 in that C star. So this is the point that we're going to be blown up. And yeah, as I mentioned, moving interior points changes the complex structure, and that corresponds to deforming the symplectic form on M sort of away from the exact one. Questions? Cool. So I know this is quite an expert audience, but there's no harm in warming up with the case of P2. So P2 is its own toric model. Here's D1, D2, and D3. And this is mirror to C star squared equipped with everyone's favorite superpotential, x plus y plus 1 over xy. So what's my triple of isomorphisms? Well, dB co of P2 has an exceptional, well, many choices of exceptional collections, but in particular, there's a favorite one by Bailenson, which is O0102, let me think of this as OD1 and OD1 plus D2. On the other hand, you can calculate by hand if the directed Foucault category of this superpotential just by sort of figuring out vanishing cycles. Oops, that went, I double clicked, sorry. By sort of finding the explicit critical points in vanishing cycles. So obviously the vanishing cycles depend. So I have my this here is my base. And I have my 3 critical points. The vanishing cycles depend on your choice of vanishing path. But I claim, and I think most people in this audience have already seen, that you can make choices of vanishing paths such that the vanishing cycles look like this. So I have the first one I'm calling V0, which is just kind of the meridian here. Oh, I forgot to say the fiber of this lattice fibration is a 3-punctured elliptic curve, which you can check. You get degrees, you come back to phi, you get degree 3, and you see that there's 3 intersections with infinity. So the first vanishing cycle is like this sort of distinguished meridian I've drawn in blue. The second one, you can check that with a suitable model, it looks like, so this green guy here, and what it looks like is the blue one, but where I've then twisted it about each of the 3 kind of distinguished meridians in my picture here. So that's V1. And then V2, the purple guy, is kind of similar, except I'm then twisting twice in each of the meridians. So if you check, I've sort of gone around kind of the first meridional component, kind of here, twice, similarly here, and kind of here. So how does that relate with P2? Well, notice that the intersection numbers of these 3 line bundles with D1, D2, D3 are 0, 0, 0, 1, 1, 1, 2, 2, 2. And in fact, that's the template. So O, this is color coded. So O is going to be mirrored to V0, OD1 to V1, OD2, D1 plus D2 to V2. And the point is that for each of them, you start with the mirror to O, and then you then twist in meridians to following this numerical data. So these numbers are going to be telling us how to then twist the meridians. So that's the first isomorphism from my triple in the introductory page. The second one is the fact that perf D is quasi-isomorphic to the Foucault category of the fiber, 3-punctured elliptic curve. This is a result of Likilian Polishuk. Is Polishuk? No. And the third one in my triple would be that coherent sheaves on C star square is quasi-isomorphic to the rep Foucault category of C star squared. And you'll be like, you're really like, okay, I know this. Thank you, lady. But the way I want to think about this for the purpose of sort of later parts of this talk is that you can get the third isomorphism by sort of combining the first 2 together with sort of sufficient levels of precision by a localization procedure. So this is the localization that was sort of, I guess, first announced or predicted by Abouzaid and Seidel, and then that got superseded more generally in the big series of papers by Ganatra, Pardon, and I'll write it out, sorry. Oh. Ganatra, Pardon, okay. On the other hand, if you're topologically minded, you might be like, well, C star square as a symplectic manifold has my favorite exact Lagrangian torus. Where has it gone in your picture with the Lefschetz fibration. And actually, it's kind of cool. So if instead of working with the Lefschetz fibration I had on the previous page that was mirror to the exceptional collection 001, 02, I can work with the kind of dual exceptional one, which I'm denoting V0 star, V1 star, and V2 star. So the reason this is dual is, well, V2 stays the same. V1, I've mutated over V2, and V0, I've mutated over V1 and then over V2. So this is the same notion as the sort of the duality notion you'd be used to if you were working with derived categories. And you can check that if you do that and you follow what happens to vanishing cycles, you get the following configuration, which is the other configuration that is sort of classically seen at kind of graduate schools and stuff for mirror symmetry for P2. So this is the 3-punctured elliptic curve where now the punctures are kind of small and the sides are glued together. And now you can see where the Lagrangian torus is as follows. So I claim that I can do, so say start with the green and the blue thimbles. So you have 2 Lagrangian disks living above these arcs in the plane. And they intersect at the central fiber here. And the pattern of intersection on the fiber is that you have 3 intersection points, like here. Am I going to find them here, which is also kind of down here, and here. Now, for each of these intersection points, I do a Polterovich surgery. So that's a sort of small local model type sort of resolution of a kind of Lagrange singularity. Or if you're an algebraic geometer, you think of the local picture, xy equals 0 gets changed to xy equals epsilon. And you can also make sense of this in the Foucault, in the sort of symplectic category. So, but what happens when I do these 3 surgeries? Well, this intersection gets replaced by a little thing like this, which is here, and similarly for the other 2. But now notice that you can just isotope this back to my 3rd vanishing cycle, the purple one. And that means that altogether, I now get an embedded Lagrangian where you sort of have like 3 disks coming out, and then the topology is concentrated kind of in the neighborhood of this orange piece. You can quite easily check that topologically it has to be a torus. Depending on how you like to think about it, you end up with the ciphered surface, the sort of 2-3 torus knot, the trefoil knot. And its exactness you can check just by doing calculations in the fiber. So as long as you, for experts, as long as you pick the same parameters for each of the 3 Polterovich surgeries, you get something that's exact. But anyway, here you go. We also have the Lagrangian torus as part of this picture. So keep this in mind for the next step, which is going to be more general. Other questions? Cool, I'll keep going. So what do we do in general? Let's first, remember everyone has a Tourette model, but I'm going to go step by step. So let me first assume that now I'm telling you about general toric pairs. So Lekilian Polishuk still applies for the fiber, and that tells you that perf of the cycle of K P1s is quasi-isomorphic to the Foucault category of a K-punctured elliptic surface. Okay, great, got that. How about a mirror Lefschetz fibration? So we know who the fiber needs to be. On the other hand, there's an analogous exceptional collection to the balanced one, which is O, OD1, OD1 plus D2, etc., up to D1 plus, and it's DK minus 1, in the same way that before, D3 wouldn't come up because then you just get the anticanonical back. And how do I write down a mirror left-shift migration? Let me give you an algorithm, and then I'll justify it kind of in 5-10 minutes. So let me write down, so I'm calling Ni the self-intersections of the Di's. Let me write down again the intersection numbers of these line bundles with each of the components of D. So this is a k-tuple of integers. And from that data, I write down my vanishing cycles. So I define the mirror left-shift migration by saying it's going to have fiber my k-puncture elliptic surface, elliptic curve, sorry. V0, which is the mirror to O, is like a reference sort of cute looking longitude. The way I've drawn this, I've got k meridians. And then to get V1, V2 up to Vk minus 1, I start with V0 and I just Dane twist in those k meridians by the number, using sort of numbers kind of encoded in here. So in practice for V1, you'd be Dane twisting N1 and N1 times in the first one, once in the second one, so this is N1, once in the second one, here's the 1, none, 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 and then right at the end, once again. For V2, which is the purple one now, I have 1 plus N1, 1 plus N2, oh, I appear to be going the other direction, 1 and a bunch of zeros, and 1 again, and so on. Is this algorithm clear? Okay, well, you can also ask questions at the end. So, and then essentially what we've done is that we have set ourselves up so that by construction, dB_co of y is quasi-isomorphic to the directed Poincare category of this vibration. So in a sense, the sort of two halves to the paper, one is constructing this left-shift vibration, where basically we're observing that full exceptional collection line bundles sort of determines a left-shift vibration for us. And then a sort of equally important part of the project is to check that this mirror space that we construct satisfies all of the properties you want, both in terms of invariance of choices and in terms of relating it to other constructions of mirror symmetry for these sort of spaces. I'll tell you more about that towards the end of the talk. But first, I owe you the sort of second half of the algorithm, which is what do you do with interior blowups? So far, we've just got the Tourette model. Oh, I forgot that I rearranged the material. I also wanted to say that there's a Stein. So remember what I just told you now was about toric pairs. And you know that the interior y minus d for toric pair is just c star square. That should be mirrored to c star square. So the total space of this left-shift vibration we construct had better be a copy of c star square, just equipped with a sort of interesting superpotential. And so the first thing is that theorem, we check that that's correct. And moreover, we identify the kind of favorite exact Lagrangian torus inside here. And it's the same idea as the one that I spelled out 10 minutes ago for P2. So we had the exceptional collection on the previous page, mirror to OD1, OD1 plus D2, etc. Take the dual exceptional collection. And now you can just iteratively Polterovich surgery, V0 dual with V1 dual, and then the result with V2 dual, etc. And I claim, this shouldn't be obvious, that doing that gives you an exact Lagrangian torus. what this is sort of saying, morally speaking, is that this dual exceptional collection is sort of distinguished in a sense, even among kind of general exceptional collections. The reason we thought to look at it is because intuitively, at least at the level of K-theory, this kind of had the properties that we wanted. Okay, so now for the second half of the algorithm, how do we deal with blowing up interior points? So remember, the kind of story on the algebraic side is I had a toric pair, and now I'm blowing up interior points on each of the components of the boundary. I'm restricting myself to that exact case, so that means, remember, that I'm blowing up a distinguished point on each boundary component. So that means if you've got multiple blowups, you end up with a chain of -2 curves, and right at the end you have kind of a lonely -1 curve. And let me say, kind of to fix numbers, that the first guy is blown up in 1 times, the second one in 2, etc., up to mk. Cool. So on the algebraic geometry side, there's a well-known recipe for getting an exceptional collection due to Bondel-Orlov, which is you start with the one we had for the toric pair. I've got to pull these guys back, sorry. And then you throw in sort of an extra generator to a category for each of for every single time that you make a blow up. So in practice, you'd have sort of pi star, this is EK indexed by MK. Oh yeah, I gave these guys names here. So maybe the precise notation will only experts maybe won't pass the precise notation in real time. But the point is, every time you blow up, you add one exceptional element, and then you pull back and you keep going. On the mirror side, here's what you do. You have V0, V1 up to Vk. This is the Flesch's fibration that I had written down for the previous case. And you add for each of the blowups, you're going to add a copy of the relevant meridian to the list of vanishing cycles. So there's M1 blowups on the first component. I add M1 copies of W1, the first meridian, etc., etc. Notice that the order of the boundary components is artificial because these meridians don't intersect, so I can mutate them over each other for free in the same way that I could mutate these exceptional objects on this side over each other for free. Cool. Are there questions about this picture? Okay, I'll keep going. So what's the general recipe? Well, let's kind of take a step back and try and sort of abstract here. So suppose I start with a full exceptional collection of line bundles. So that's not quite what I had on the previous page, but if I mutated these kind of extra guys in these columns just over O, I would get line bundles instead. So suppose you're given any full exceptional collection of line bundles for dB co y, say E0, E1 up to En. given just the data, this data here, I can write down a Weinstein Lefschetz fibration with the following data. So the fiber is going to be sigma. So sigma is just determined by, so this is a K-punctured elliptic curve. And K is the number of components, various components of D. So that's sort of clearly determined. And then vanishing cycles. There's going to be one for each of these guys, given by the following algorithm. So my EIs, if you restrict EI to D, the boundary guy, because we're working with this distinguished complex structure, there's very little, there's the sort of, the restriction of EI to D is sort of determined by the numerics of the picture. So it's just going to be OD and a sum of, with a divisor which is a sum of points. So this is the distinguished point, which we were blowing up. And then the number of times is just EI dot DJ. And on the mirror side, we put LI, sort of use with the algorithm from before. So I start with V0, and then I'm going to Dane twist it in the vanishing cycles. Sorry, I'm going to Dane twist it in meridians, where the number of Dane twists is going to be precise. The number of Dane twists in the jth meridian is going to be precisely given by Dij, this intersection number. So that's the algorithm. Sort of, if you wanted to think completely generically. Now you can start worrying about the kind of questions I was mentioning before, like what happens if you pick a different collection? So I haven't put that many details in these slides, but so there's obvious sort of ways of changing full exceptional collections, right? So for a start, you can mutate and wonder, well, what happens if I do sequence of mutations and I happen to come back to something that's also full exceptional collection line models? The answer is, well, those two mirror Lefschetz fibrations are going to be related by a sequence of Lefschetz fibration mutations. In particular, even though the description of a fibration changes, the fibration itself does not. Similarly, you could dualize your full exceptional collection. We also kind of study what that does to the fibration and check that it sort of gives you a sort of dual description of the same fibration. And maybe the most interesting thing is the sort of invariance on choice of Tourette model. So one thing I didn't go into at the start is the fact that a Tourette model for a log Calabi-Yau surface is essentially never unique. But what we do know from sort of work of Blanc and Korte-Kalagiras is that given any pair of Tourette models from the same log CI surface, one can get between them by basically a sequence of prescribed moves. And there's essentially two types of moves that you can do. And for both of them, we sort of understand what they do to the Lefschetz vibration and sort of check that the overall fibration, the overall space when relevant doesn't change. Other questions about this? Okay. So in particular, you could ask, well, remember how you had this sort of Tourette model D? Well, sorry, this D was the cycle. And one of the things you were doing was blowing up a corner. That, let me draw it here. I'll probably put the wrong number. That corresponds to something called the stabilization of the mirror Lefschetz fibration. So obviously the fiber changes because the number of punctures goes up by 1. But in fact, the total space, so here the interior of the complex surface doesn't change because you're blowing up at the boundary. And so you'd expect to have a mirror Lefschetz fibration where the fiber is going to change, but the total space of the fibration shouldn't change. And that's correct because it's mirror to a sort of well-known procedure for Lefschetz fibrations called the stabilization. On the other hand, if you did an interior blow up, let me just point out that if you do an interior blow up, that does change the total space of the fibration, right? So now for the mirror symmetry part. Well, this, for sort of general reasons, basically based on what the definition of the directed Foucault category is. Sorry, I thought someone knocked on my door, except this building's empty, so I think it's just the wind. So dB co of y, essentially by construction, things are set up so that this is quasi-isomorphic to the directed Foucault category of the thing that we define here. And of course, we still have the Lekili-Polishuk result kind of relating perf D and the directed the Foucault category of the fiber. Those isomorphisms are sort of naturally compatible sort of at DG level, or as A infinity bimodules to be technical. And in particular, the sort of Abouzaid stroke Galatropon-Shende localization process just applies to give us that dB co y delete d is the derived rep Foucault category of M, where M is the total space of this guy here. Questions? Okay, so now let me tell you, oops, I practiced and forgot to leave this. Let me tell you about how to relate this to various of the existing constructions. So for log Calabi-Yau surfaces, there's kind of a very clear expectation for what the mirror should be from sort of the perspective of SYZ rather than homological mirror symmetry. So how is it described? Well, this picture that I have here is basically you should think of as the base for enormous toric fibration. And I put in rays corresponding to the toric fan for, I think it was called Y prime bar, D prime bar. The point is this is the toric pair in your toric model. And then I introduce singularity. Oops. Sorry, I touched the wrong thing with my hand. And then I put singularities in this almost toric fibration for each of the interior blow-up points. So the picture you should have in mind is each of the rays of the fan corresponds to one of the irreducible components of the toric boundary divisor. and you were blowing up M1 points on that, and you put kind of M1 critical points on that fan, on that line array. And this, the other reference I put, so this sort of the perspective sort of expected from Gross Hacking Keel, even though they didn't prove that mirror spaces actually have such almost toric vibrations. And you can learn a lot more about this sort of process in kind of earlier work of Symington, sort of setting up the whole theory of almost toric vibrations. And from this perspective, sort of morally speaking, what mirror symmetry does is that you start with an almost toric vibration, and to get the mirror, you just rotate all of your invariant lines by pi over 2. And so what that gets you is now, well, basically you take the same picture, but now you interpret these lines as kind of being sort of Lagrangian-ish directions, and as being sort of the invariant directions for the vibration. So in particular, above, for instance, the set of segments in these directions, you'd have sort of Lagrangian symbols going into the relevant to all of these critical points. And similarly for the other rays. In particular, at the topological level, what does the mirror, well, sort of symplectic topological mirror level, what does the mirror look like? Well, you have an central fiber here. This shouldn't be the same purple. Let me pick another color. Here's green. So this is a T2. And you'd have sort of a neighborhood of this, which is like a T star T2. And then for each of the critical points, you glue on a Weinstein handle, which is like T star of a disk. So you should think of the disk as being like this orange symbol, or similarly, this one, or these ones, etc. And this picture is telling you how these are glued. So the data that you need in order to make this Weinstein handle attachment is that, morally speaking, the boundary of this 2-disk should be some sort of co-oriented curve on T2, and its slope. So like now think of T2 as actually living in my lattice R2, like it was being a quotient of the lattice R2, and the slope of boundary of this is an S1, right? The boundary of the disk, that its slope should be perpendicular to the ith ray. Hopefully that wasn't too quick or too technical. But the point is that, so well, first of all, theorem is that we prove that this is Stein equivalent to the guy we construct. So this is the total space of the Lefschetz vibration. The meta perspective is one about sort of compatibility between SYZ and homological mirror symmetry. Because morally speaking, the SYZ expectation was the mirror should be the total space of the following almost toric vibration, described as I was telling you up here. And what we prove is that the mirror that we construct is quasi-isomorphic, Stein equivalent. Of course, our guide doesn't come with an almost toric vibration to R2, but of course, if there's Stein deformation equivalent, then you can just kind of transfer the one on here, and that ties back onto a bunch of perspectives, including in particular sort of ideas in the Gross Hacking program on GHK. Let me point out, since I have a minute or two, that from this picture, it's quite easy to see, or to sort of get intuition of what happens if you were to deform away from the distinguished complex structure. I mean, the complex structure that is mirror to the exact symplectic form, because that corresponds to keeping kind of the same invariant directions, but moving the points away. So something like, imagine something like this. So these, you imagine these purple points just kind of being deformed away a bit. And so if you do that, so remember before I had thimbles, but in particular, above this segment here, you have a Lagrangian sphere, because it's the same. The thimble has the same vanishing cycle at both ends. But once you deform away, topologically, you still have. This isn't pretty. Give me a sec. Topologically, you still have a thimble, kind of like this. But now that thimble has non-trivial symplectic area, which is basically sort of an incarnation of the distance between the two invariant lines. And that you see that way that the integral of the symplectic form on that homology class is no longer 0, so it's no longer exact. Questions? Okay, so I have a few more things to say. So the next thing I wanted to say is this. Well, this ties to quite a lot of stuff. In particular, there was another side thing I wanted to say, which is I mentioned earlier different types of changes of Tourette models. So for experts in this kind of almost Tourette picture, you might be used to doing sort of what sometimes they're called Symington moves. In particular, there's a natural deformation where you take a critical point and you sort of just push it sort of beyond the central intersection point. So this gets called a nodal slide. And for us, that's mirror to a change of Tourette model. So we understand the changes of Tourette model at the level of the Lefschetz fibrations, and we also see kind of at least the residual ones at the level of the SYZ picture. Moreover, I have here this. So I've already got for myself one exact Lagrangian torus, kind of the T2 coming from the sort of central point here. But one of the things that we know about log Calabi-Yau, specifically surfaces, is that they're all cluster. So one of the things that GHK study is the fact that all of these admit sort of cluster structures. So that these all admit cluster structures. On the other hand, this description of the mirror, as you know, just T star T2 with these Weisner handle attachments, is precisely what comes up in work of Shinitrim and Williams, who show that this space admits a sort of cluster varieties worth of exact Lagrangian tori. The one thing that is sort of coming out basically in the wash for free from this work is the fact that via mirror symmetry, these two cluster varieties, the one, y prime minus d prime, and the sort of moduli, this sort of big piece of the moduli space of exact Lagrangian tori, these are just the same. These are just the same. And one standard way to translate it is sort of very nice work of Pascal Tourette, which sort of tells you, sort of studies sort of individual mutations. Let me give you a tiny bit of geometric intuition for this picture. So morally speaking, what you're doing just with let me do one of these handle slides. So I take this guy and I imagine sliding over here. And that corresponds to a mutation. Now you have a new picture where you're still going to have a sort of central Lagrangian torus fiber, which is still going to be exact. But now that's mirror to a different T2 because of this mutation process. And the torus that you have on this side, so topologically, is given by starting with this T2 and then sliding it. So there's a sort of purely symplectic sort of slide procedure in this picture where you slide your T2 over a disk to get another exact Lagrangian T2. I have a few more slides sort of beyond the thank you page, sort of extra details that I wasn't sure whether or not I would get to. But no one ever told me whether this was sort of 50, 55 or hour-long talk. So how about I stop now, and then that way I can focus the sort of extra information on whatever details people are most interested in. Thank you.
All right, thank you very much. Questions? Well, if there are no questions, let's thank Ailsa again. And we will proceed with talk by Tony Pantev at 10:30 a.m. Eastern Standard Time. See you then.